we doing? Good. How's the weekend? Good. I think you're that. What questions do you have? Yes.
The homework from last night?
Yeah.
Can we go over any of that or talk about any of that?
Did you have one of the a specific one you wanted to look at?
How is... Hold on, sorry, I should pull this up.
All right.
Definitely one of the first.
Let me get to the assignment. And then you can point to me what you want to see. Sometime today. Did you have one in particular?
I'll just look at it. I think number 3.
The third one?
Yeah.
Okay. That one?
Yeah, the determine the x and x. Was that just use the quadratic formula or is that the new
That's you'll want to use on that particular one. You need to use the quadratic formula because you want to set it equal to 0 and solve, and that one won't factor.
Yeah, but whenever I was doing the quadratic formula, I was doing 48 in the, I guess it depends on, but I wasn't.
Yeah, because it changes the numbers depending on which one you have.
But I just wasn't getting it right.
I can check yours and see.
Okay.
Yeah, I can do that. I don't want to pull it up in front of everybody, obviously. So, but that's exactly what you would do. You would set it equal to 0 and solve. So, sounds like you were doing it correctly as far as that goes. Yeah. I'd have to look and see what your answers were to see if I can guess what maybe you did wrong. But yeah, that's exactly what you're supposed to do.
And then the last one was kind of confusing too.
The last one? Okay. That one?
Yeah.
Okay. So it's trying to make a gutter, and was it the problem finding the function?
The problem with finding the function, it was how, like, because we didn't have numbers to plug into, because whenever I was looking at our notes, we had, like, x or whatever equal this to plug in. And I just didn't know what to plug into the function to be able to get out x. Or, I just didn't know how to do that.
Okay. So it tells you had 50 inches of stuff to work with. And you want to fold it into a gutter, and eventually you want to get the maximum area in there. Okay, so I'll write on the board. Right off to the side here. So to make the gutter this direction, I've got to fold up both sides evenly. Otherwise, I'm not going to get a gutter. I'm not going to get a gutter. I don't know what I'm going to fold up yet, so I'll call that an X. If I know that I had 50 to start with, and I take an X from here and an X from here, what's going to be left here? If I move one X up and another X up, how much is going to be left over here?
Whatever. I don't know whatever. Yeah.
It'll have an X in it. It'll have an X in it for sure. If this were 10 and this were 10, what would that be? 30, right? Because I had to take that X and that X and take it off of there, right? Mm-hmm. So if it were 5 and 5, it would be 40. So if it's X and X, I'm going to take off the 2X from the 50. So that's where the 50 minus 2X comes from. Okay. So now, if I want the area, I want to know what this area is in here. What would the area be?
Would it be what we got up there with the x?
Yeah. Yeah, it could be X times the 50 minus 2X. Or 50X minus 2X squared. Yeah. And then from there, to figure out the maximum, the X value for the maximum and the maximum actual area, we'll want to use our minus B over QA part to figure out the X value. So what's the b in this case?
The B or the B?
The b,
The
sorry.
B, it would be
50 and the a is
2.
-2, right? Yeah. So what is it, 12 and a half? Looks like. Just what they got up there. Yeah. Yeah.
And then would that be plugged into the inches squared too? Okay.
Yeah, you'll put the 12.5 into the function to figure out the maximum. Yep, that's right. Yep, welcome. Other questions? Again, if you've got a question on the homework as you're working through it and want something explained, take a screenshot of it and email it to me. I'm happy to answer questions that way. What I would not do is click on the Ask Your Teacher button because it sends me an email about a day late. So if you have a question about the homework, please take a screenshot and email it to me and I'll get it instantly versus do the Ask Your Teacher function and then it doesn't ever send it to me. Even though I have it set up to say, forward it to my email, it does it about a day later, which is not helpful to anybody. So, again, if you've got questions on the homework as you're working through them, snap a screenshot of it and send it to me. I'm happy to answer. Other questions? Okay. Well, let's continue on then with our chat about polynomial functions in general. And we started talking about end behavior last time. And again, end behavior is a discussion of what happens on the tails, what happens on the left-hand side, and what happens on the right-hand side to your graph. Not what happens in the middle. A discussion of what happens in the middle, we'll do a little bit of that as well, but more of the discussion of what happens in the middle of the calculus type of thing. So we'll have a couple of ways that we can talk about what happens in the middle, but generally speaking, you need calculus to do a real good analysis of what happens in the middle. So we're only worried about what happens on the ends. What happens as x gets really, really large in the positive direction? What happens as x gets really, really large in the negative direction? And that's what we meant by that notation that we talked about at the end of class. Since we're interested in what happens with x with the function as x gets really, really large, turns out the only thing we need to worry about is that leading term, because that's the highest power of x that we see. The bigger x gets, the bigger that power of x is going to get. It's going to dominate every other term in the polynomial. So to determine what we refer to as end behavior, we only need to look at the leading term. So if we had something like, let me just do this off to the side quickly, and then we'll do a summary table. If you had f of x equals, say, 4x to the fourth, and not worry about any other terms, just look at 4x to the fourth, ignoring the 4, what does that look like? Does they both point up, or does one go down and one go up? Both up, right? What tells you that? Yeah, the fourth power, the even part, right? So I know from the fourth power that they both go up. From the 4, does it flip it upside down or does it stay up? Stay up, right? So notice that when this is positive and even, both tails are going to point upward. Okay? So the way we would write that, and this is how we write end behavior, we would say as x goes to negative infinity, f of x goes to positive infinity. As you go to, this says as you go to the left, the function goes up. That's what that says. Okay. As x goes to positive infinity, the function also goes up. Okay. That's how we're going to write our end behavior. But again, we're just interpreting that from the graph, right? Our graph looked like this. Kind of. My axis is goofed up, but that's what the graph looks like, right? And this says as you go to the left. So as we go to the left-hand side, this says that your function is going up. The bottom statement here says as you go to the right, the function goes up. Okay. What if I wrote something like f of x equals negative 3x to the 7th. Do the tails both point the same way, or do they point opposite ways? Opposite, because the 7 is odd, right? So originally, it would go from lower left to upper right, right? What does the negative do? Flips it, right? So I know that this graph should look like that, right? You probably don't have it steep enough or on the ends or flat enough in the middle, but it should look like that, correct? Kind of looks like x cubed, a little bit steeper on the ends, a little bit flatter in the middle. And the negative flipped it upside down. Okay. So again, if we write this in symbols, as x goes to negative infinity, that says as we go to the left, which way does f of x go? Infinity. It goes up, right? As x goes to positive infinity, what does the tail do? Negative infinity. It goes down. Okay. So notice that all we've looked at is the exponent even or odd, and is the leading coefficient positive or negative? So that's exactly what we're going to do to fill out our summary table here, is when we've got our function, if the leading term is a sub n x to the n, then we've got something different that happens if n is even or n is odd, versus if the leading coefficient is positive or the leading coefficient is negative. Okay. Again, all of this is based on a leading term. If the degree is even, if the power on x is the highest power of x is even, we said both tails point which way? Up, right? The same direction, right? It's up if it's positive. So the way that we write that is as x goes to negative infinity, f of x goes to positive infinity, and as x goes to positive infinity, f of x goes to positive infinity. The way the graph should look is something like this. Again, this is end behavior. I don't know what happens in the middle. End behavior just says what happens on the tails. That's why I've got those dots in the middle. All I know for certain from looking at the leading term, right tail goes up, left tail goes up. What happens if we go to fill out the next piece of the table on the right? Since n is odd, do they both point the same way or both point opposite directions? Opposite, right? Since it's positive, does it get flipped upside down? No. So we should have something that looks like, on the tails again, we should have something that's pointing up on the right, down on the left, and I don't know what happens in the middle. So how do I fill out these statements? As x goes to negative infinity, good, f of x goes to negative infinity, good. Because again, the statement as x goes to minus infinity means you're going to the left. As you go out to the left, the function is pointing down. How do we finish off the second statement? As x goes to positive infinity, what does f of x go to? Positive infinity, good. And I wrote negative to start with. Before we write it out in symbols, what happens to your pictures if instead of having a positive leading coefficient, we have a negative leading coefficient? What happens to the pictures? They flip upside down, right? So this one, both tails will point down. This one, oh, I drew too big of a picture. This one will point up. This one will point down. Again, I'm putting dots in the middle because this is not a discussion of what happens in the middle. This is what it is, a discussion on what happens on the ends as x gets big, either positive or negative. So when you're asked about end behavior again, you're basically asked two questions. What happens as x goes to negative infinity, and what happens as x goes to positive infinity? In both cases, what happens in this when n is even? That f of x goes to negative infinity. Again, all of this saying is, I'm just trying to say it in words as well. As x gets big in the negative direction, as you go to the left, the function goes down. The graph points down. As you go to the right, the function also points down. That's all it's saying. What about this last case? As x goes to negative infinity, what does f of x go to? Infinity. And as x goes to positive infinity, f of x goes to negative infinity. Good. All we're doing with this discussion is using math symbols to describe what we see on the graph, or using math symbols to just what I'm saying in words, right? You go to the left, you go down, go to the right, you go down, or up, or what have you. Questions on how we filled out the table? So far, so good? Great. So let's just look at the next couple of examples. These next couple of examples ask you to determine the end behavior. So literally it's just that summary statement with the symbols. Again, if we're interested in end behavior, what do we look at for the polynomial? What's the leading term, right? For this first one, what's the leading term? So negative 4x cubed. Yep, good. So our leading term here is negative 4x cubed. So the degree of the polynomial, just to remind us of the words, what's the degree of the polynomial here then? 3, because that's the power, right? What's the leading coefficient? Negative 4. Good. Okay. All right. Since the degree is 3, what happens with your tails? Same direction or opposite direction? Opposite. Good, because it's odd, right? So let's go ahead and write our statements then. I've got 1 as x goes to negative infinity and 1 as x goes to positive infinity. Remember, they're both pointing opposite directions, right? One's going up, one's going down. Originally, it would go this way, right? From bottom left to upper right. But since it's negative, it flips upside down, correct? So as x goes to minus infinity, what does your function go to? Positive infinity, good. And as x goes to positive infinity, f of x goes to negative infinity. And again, basically what you should be thinking of is, you don't have to draw this down, I'm just writing it off to the side. F of x equals x cubed would look like this, wouldn't it? Kind of that base graph idea again, that's what x cubed would look like. So if you make it negative, it would flip it upside down. And that's what we're basing our answers here off of. Does that make sense? I'm not worrying about the rest of the polynomial. I'm not worried about what the actual number is in front. I'm I'm just worried about, is it positive or is it negative, to tell me if it's flipped upside down or not. And that's it. When you're asked about determining the end behavior, it's looking for statements like this. Okay. Let's look at the second example. Again, what tells you about end behavior? The leading term, right? That leading coefficient and the degree, correct? Leading term here is what? 12x to the 6. Good. That's the piece that we're interested in. So looking at that leading term, tell me about the tails. They're both going in the same direction, and since the leading coefficient is positive, they're both going up. Yeah, they're both going in the up direction, right? So writing that out in symbols. As x goes to negative infinity, f of x goes to positive infinity. And as x goes to positive infinity, f of x goes to positive infinity. Good. They're both going the same direction, and they're both going up. Yeah? Questions on this? Again, if you want to think about it from a base graph idea, your f of x equals x to the 6th would look like something like this, right? Roughly. Did it flip upside down? No, because it's not negative. So that would be what you're basing your answers here off of. Goes up to the left and up to the right. What questions do you have on that? All right. So I said we're not going to do a lot of analysis on the inside. Our discussion of the end behavior talks about what happens on the tails. And then we're not going to do a lot of analysis on the inside, but we're going to do a little bit of analysis. So some of the things that we might be interested in to help us with graphs of polynomials in particular is where does it cross the x-axis? And that was what we mean by a zero of a polynomial. Graphically, that's what's going to help us tell that. But from a numeric standpoint, we say something is a zero if when I plug that value in, I get 0 out. That's what we mean by a zero of a polynomial. If I plug the number into the polynomial, I get 0 out of the polynomial. So there might be some other ways of asking about zeros. So just make sure we have all the terminology down. Another way to say that C is a zero, we might say the words C is a root of the polynomial. That's another way we might say it. We might say that C is a solution of f of x equals 0. So root, solution, 0 all mean the same thing. I will say root quite often versus 0. Make sure that you know that root means 0. Graphically, again, remember when we plot a function, you plug in the x, you get out the y. So if C is a 0 or if C is a root, the point C comma 0 has to be on the graph. That means that the point is on the x-axis. So from a graphical perspective, x equal to C is an x-intercept of the graph of y equals f of x. This is another reason why they use the word root for a 0. If you think of the x-axis as ground level, if you will, the graph is rooted on the x-axis. The last one is something that we're going to be interested in a couple of sections from now. If you were to factor the polynomial, remember doing factoring, right? Breaking the polynomial into pieces. If you were to do a factoring of this polynomial, then you would see x minus c is a factor of the polynomial. If you were trying to break the polynomial down into factors, if c is a 0, then x minus c is a factor. And that makes sense if you think about writing it this way. If I have f of x is x minus c times something else, doesn't matter what this extra piece is on the end. If I put c in here, you would put c right here. What's c minus c going to give you? 0, right? So it makes sense that x minus c would be a factor in that case. But again, these are just other ways of saying that you have a 0. You might have a solution to an equation. You might have a root of the polynomial. You might have an x-intercept of the graph. You might have a factor in the factorization. All right. This one has a typo. It's going to make this a little bit easier. I forgot the x on that last term. There should be 75x there. So this one asks us to find the zeros. And this is a lead into something that we're going to do later on, is basically trying to factor this as much as we possibly can. And that's why I want to make sure I put the x on here. So when we want to find the zeros, it's asking us to solve this equation, set it equal to 0, and find the x values that make it equal to 0. When factoring something, what's the first thing you should look for? Yeah, greatest common factor, right? What do you see as the greatest common factor here? 5x. And as a matter of fact, I'm going to go ahead and factor out a negative as well, just so I have just a positive x squared when I'm left. The first term is x squared. If I factor out a 5x. You told me x. If I factor out negative 5x, what am I left with in the second term? Negative 2x, good. Right? Because I took out a negative, so it'll flip the sign. What about the last term? What are you left with? Negative 15. How does that polynomial factor? Yeah. Since it has x squared, it better have x and x. I got a minus 2, so I need to use a minus 5 and a plus 3 in the middle to get negative 15 and add to negative 2. So the 5x piece gives you what for a 0? This piece right here gives you just 0, good. The second factor gives you I put the plus 3, yeah. Negative 3, good. And the last piece gives you 5, right? Remember again, when you have it factored, I didn't write it out, but remember when you have it factored, you set each piece equal to 0. Right? That's what that means. So these would be your zeros then. This would be your final answer. That's what the zeros are. So far, so good? Questions on that one at all? Make sure if you are rusty on your factoring to go review some factoring. If you need some factoring practice, let me know. I can get you some factoring practice too. Okay. All right. Let's do the next one. It says using n behaviors and zeros, let's sketch a graph. And this is what we're going to try to do here for the rest of the section. Let's do n behavior first. What tells us about n behavior? Yeah, the leading term, which in this case is the negative x cubed, this piece right here, right? So for your end behavior, whoa, see if I can write it correctly. We have a statement as x goes to the left and a statement as x goes to the right. You told me that the leading term is negative x cubed. So do the tails point in the same direction or opposite direction? Opposite. Good. They go in opposite directions. Since your leading coefficient is negative, does it go lower left to upper right or upper left to lower right? Upper left to lower right, right? It's basically x cubed flipped upside down, right? Okay. All right. So as you go to the left, as x goes to negative infinity, f of x goes which way? Positive infinity. Good, because we just said it was upper left, right? As x goes to positive infinity, f of x goes to negative infinity. Because again, we said lower right. Does that make sense for the end behavior? Yeah? Okay. Finding the zeros, we set the function equal to 0. So we want negative x cubed minus 2x squared plus 9x plus 18 equals 0. This one, there's no GCF in this one, so we don't have anything to factor out. Well, there is a GCF, it would be 1. There's nothing to factor out of this one. This is a 4-term polynomial. Kind of one technique to try to use to factor a 4-term polynomial. What that is. Yeah, grouping. That's exactly right. Group the first two together. Group the second two together. What do you see that you can factor out of the first two terms? Just looking at the first two terms by themselves, what do you see? Yeah, negative x squared leaves you with x. Yeah, since we factor out the negative side, it'll be x plus 2. When you're doing factoring by grouping, inside that group, that x plus 2, I want to see it in the next set of 2. Otherwise, I'm not going to be able to factor it. What can you factor out of the next set of 2? A 9. What are you left with? X plus 2. Now the factoring by grouping part says I take out the x plus 2. Now I have a GCF essentially. When you take out the x plus 2, what are you left with? Good. This is now the GCF of those two terms, if you will. Factoring that GCF out, you're left with negative x squared in the first part and 9 in the second part. This thing, I think, factors a little bit more. Should have left a little bit more room here. Let me write it as 9 minus x squared to start with. What do you recognize that 9 minus x squared as? It's a difference of squares. Cool. How does that factor then? As it's flipped around, it would be 3 minus x and 3 plus x, right? Like I said, if you need practice on your factoring, please do. And if you need some extra practice on your factoring, let me know. I can get you some. I got plenty. I got lots of factoring problems. As a matter of fact, I have a computer program that'll randomly generate factoring problems. So if you need factoring problems, I can get you thousands. Okay? I'm not joking, literally thousands. All right. What makes the first factor equal to, if I look at that x plus 2, what makes it equal to 0? Negative 2. If I look at 3 minus x, what does that make? What makes that 0? 3. 3 plus x? Negative 3. So there are your zeros. So we've done end behavior, and I've done zeros. Now it says, let's make a graph. Okay? And surprisingly enough, we can get a pretty decent graph out of this. Get something in my eye. The end, we know that if I put some scale on here a little bit, I'm not going to worry about my vertical scale. I'm just worrying about getting a rough shape of what this function does. The zeros tell me where the graph crosses the x-axis. So I know we cross at -3, we cross at -2, and we cross at +3. And for some reason, it erased my tick mark. Apparently, when I do something like that, I think I'm trying to scribble something out, so it just makes it disappear. All right. Where do we put those zeros is where it's going to touch the x-axis, right? Okay. So the end behavior, we had that too. You already told me it went from upper left to lower right. So when I start drawing this, I'm going to start drawing it from the upper left. Because you just told me that a little bit ago, right? Okay. So we'll come down from the upper left. We'll go through x equals -3. Come down, turn around, go up through x equals -2. Go this way, come down through -3. And then we know we also went to the lower right, so we went all the way through. Again, rough shape, right? I didn't draw anything to scale in the vertical direction at all. But then if you put this in a calculator, put it on a computer and graph it, this is pretty close to what we have, not worrying about the vertical scale. Okay. There is one more point we could have also put on this graph to help us a little bit more. Where does this function cross the y-axis? What would you, yes? Oh, sorry, I thought you were asking a question, sorry. Where would this function cross the y-axis? What would you put in for x to figure out where it crosses the y-axis? 0, right? Because the x coordinate is 0 on the y-axis, right? What do you get when you put 0 into that function? 18. I get the constant term, don't I? So I know that this thing would also cross at +18 right here. Gives me a little bit more information about the graph. And this is what we're going to be looking for when you're asked to sketch a graph. Not perfect, just get the important pieces down. Okay? Now, in this case, we went right through the x-axis, back up through the x-axis, and down through the x-axis, right? That may not happen all the time. For example, you've seen things that come down, touch the x-axis, and go back up again, right? Didn't cross it, it just touched it. As a matter of fact, what's a prototypical example of that? What kind of graph did I just draw? That looks like x squared, doesn't it? Okay. Sometimes when you draw it, it does flatten out, but it still crosses, right? It didn't go straight through it. It flattened and then crossed, right? What does that remind you of? X cubed, right? Notice that x equal to 0, that should be an x. It was an x, I just didn't make it look like an x. Notice that x equal to 0 is a 0 of both of those functions, right? You put 0 in, you get 0 out. But notice that when I've got an x times an x. If you think of them as factors, I see 0 twice essentially, don't I? This one, I see 0 times 0 times 0. I see it 3 times, don't I? That's the concept of what we mean by multiplicity of a 0. Okay? So, over here, when we say we have a multiplicity of m, what we mean by that is that x minus c to the m is a factor, but x minus c to the m plus 1 is not. That's what we mean by the multiplicity. Okay, so rather than harping on the definition, let's look at the example, and I think it will make a little bit more sense. Okay? Here's a polynomial already been factored for you. It's x plus 4 squared times x minus 1 cubed times x minus 5. And it wants to know what's the multiplicity of each zero. Okay? Well, first, let's identify the zeros. Again, if you set this equal to 0, what makes this first factor equal to 0? -4 does, right? Put in -4 for x, I get 0 out, don't I? What makes the second factor equal to 0? 1. What makes the third factor equal to 0? 5. Good. So that's why we want to do this factorization. It helps us identify what the zeros are. Okay? We okay with the zeros? We'll do the multiplicities in a second. Are we okay? We see where the zeros are coming from. Yeah. Okay, cool. All right. Multiplicity says, look on the power of the factor that the 0 came from. Okay? All right. -4 came from this factor, did it not? Did it not? What's the power on that factor? 2. So the multiplicity of -4 is 2. One came from this factor. What's the power on that factor? 3. So what's the multiplicity of that 0? 3. Good. Finally, 5 came from this factor. Yeah, the power on that factor is 1, so the multiplicity is 1. Okay. So -4 has a multiplicity of 2, 1 has a multiplicity of 3, and 5 has a multiplicity of 1. Okay. All we're doing, we're identifying the multiplicities, is we're just looking at the power on the factor. That's it. Okay. Now that's going to give us more information about the graph, but that's all we're doing for this part. Do we have questions on that one? We're going to do more. We're going to do more of it as we go along. But like I said, I think it was a little lot easier to identify what's going on rather than me writing a long-winded definition. Okay. All right. Let's look at the next example. Talk about what the behavior has to look like, and then we'll do another example. All right. What happens? Okay, so I've already talked a little bit about crosses versus touches. Right? If I go back over to what I drew up here a minute ago, when I have something that comes down, like this one did, it came down, touched, and went back up again. That's a touch, right? It kisses off the x-axis. It kind of reflects off the x-axis. Versus a cross means that when we actually hit the 0, we went from one side of the x-axis to the other. That's what I mean by crossing versus touching. Well, what do you notice about the power on the x that told us here whether it crossed or touched? It was odd or even again, right? Okay. So this is what the multiplicities tell us about. So if the multiplicity is even, it touches. If the multiplicity is odd, it crosses. And what I mean by that is that the graph touches the x-axis. The graph crosses the x-axis. That's what I mean by this. I'm talking about the graph, right? That's why I've got the label of behavior of the graph. All right. The other part is, when does it flatten? Well, let's go back up here, looking at the graph again of the last two. Would you say that this graph flattens out at 0? Is it flat right there? Yeah, it's pretty flat, isn't it? How about here? Does it flatten here too? Yeah. As a matter of fact, if you do x squared, x cubed, x to the 4th, x to the 5th, they all flatten at 0, right? The only time it doesn't flatten it at 0 is if you had f of x equals x. It crosses right through it, doesn't it? Okay? So we say that it flattens near, this is all in the same label, flattens near a 0 if the multiplicity is greater than 1. Okay? So let's see if we can put all this information together and do this example. All right, so notice that this is already factored for you, so we have to do a little bit of thinking to answer some of these questions. Okay? The first question here says, what's the degree? Well, if I want to know what the degree is, I have to know what happens if I multiply this all out. Do you think I expect you to multiply this all out? No, it'd be a lot of work, right? Remember, the degree is about the highest power of x that you see, right? Okay? If you actually squared this term out, the highest power that you would get would be, if I just squared this out, what would be the highest power of x you get? X squared, right? How about from this one right here? Just an x. This one you would get x cubed, and this one you get an x. What do you get when you multiply x squared times x cubed times another x? X squared times x cubed times another x. X to the 7th, all right? So what's the degree going to be? Yeah, the degree is the number, so it would just be 7. Good. Basically, what can you do to figure out the degree? Yeah, add those exponents, right? Just add the exponents. That'll give you the degree. 2 plus 1 plus 3 plus 1 gives you 7. Right? Okay. All right. Again, if we multiplied it all out, the leading coefficient is on the highest degree term. Well, that x squared would have a 1 on it. That x would have a 1 on it. That x cubed would have a 1 on it. That x would have a 1 on it. At the very, very end, you'd multiply it by what? -3. So what's the leading coefficient? It's -3, isn't it? Right? You have 1x times another 1x, and so on up the line. All right. So the degree is odd. The leading coefficient is negative. Right? So let's see if we can write down the end behavior. Okay, so as x goes to negative infinity, x goes to positive infinity. Again, the degree is even or odd? Odd. So the tails point in the opposite direction. Leading coefficient is negative. So does it start lower left or upper left? Upper left, right? So as x goes to negative infinity, f of x goes to infinity. As x goes to positive infinity, f of x goes to negative infinity. All right, we're out of time, but see if you can figure out at least D through G. This is what we were just talking about a little bit ago. And then we'll talk about how we get a rough sketch next time. Okay? And then we'll do the last example as well. So for Wednesday, see if you can get through D, E, F, and G. If you want to get a little bit of a head, go to the next example and go through the same answers. And then we'll go through that next time. All right? Have a good one. We'll see you on Wednesday.